In this problem, we're going to work with a relation again, and this relation is going to be on A. So when we say it's on A, we mean it's from A to A, so it starts on A and ends on A. And what we're going to practice in this problem is going to work on representing R as a directed graph, and also talk about some of the properties of the relation R. So we're going to represent R as a directed graph, and here's the directed graph we're going to use. So there are the kind of the nodes 1, 2, 3, 4, and these directed edges describe the relation R. So depending on where you start and where you end up, this is essentially describing the elements of the relation R in a graphical form. And by looking at this, we can actually write down the elements of the relation R in set notation. So the first thing we're going to do is write the set R from looking at this directed graph. So the way I like to do this is I like to basically start with each node in order. So I would start with the node labeled 1, and I would see, from the point 1, where can I get to? So starting at 1, I can go from 1 to 2 because there's an arrow going from 1 to 2. So one of the elements in the set R is the coordinate 1, 2. Similarly, starting at 1, I can go to 3. So the element 1, 3 is an element of R. And those are all the places that I can get to from the point 1, so we're done with 1. And now let's go to 2. From 2, where can I get to? Well, at 2, there isn't anywhere that I can get to. There's nothing that leaves node 2. So there are no elements that start with a first coordinate of 2. What about number 3? Well, starting at 3, I can go to 4. So starting at 3, I can go to 4. So 3, 4 is an element of R. And that's all I can do with node 3. And then node 4. There are lots of ways that I can start at 4 and go somewhere else. I can go from 4 to 1. I can go from 4 to 2. And I can go from 4 to 3. So all of those are elements of the relation R. So looking at the directed graph, we have written down the relation R. So we're done with that. Now let's talk about some of the properties that relations might have. One of these properties is what we call reflexive. So one question we have is R in this specific instance reflexive? So let's recall what the definition of reflexive is. It says that for all elements in the set A, we need x, x to be in R. Okay, so we can answer this question now from this definition, and very clearly the answer is no. This example that we're working, the relation, the set that we just listed, is not reflexive because there are several elements in A that we don't see listed as x, x in R. For instance, the element 1 is in A, but the element 1, 1 is not in R, which is what you need to be reflexive. So there's one point that we find that basically violates the definition of being reflexive. So no, this relation is not reflexive. We could just have easily have written down 2, 2. We need 2, 2 to be in R if R is going to be reflexive. So it also fails because of that point. 3, 3 is not an element. 4, 4 is not an element. So there's actually lots of elements that make this relation not reflexive. What about symmetric? Is this a symmetric relation? So what do we mean by a symmetric relation? We mean that for all x and y in the set A, x, y in R implies y, x in R. So again, just by looking at the set that we've written down for R, we can quickly conclude that this is not a symmetric relation. For instance, the element 1, 3 is in R. We listed it in our set. If this was a symmetrical relation, we need to have 3, 1 in R. But 3, 1 is not in R, so this is obviously not a symmetric relation. And again, there are many others that we could have chosen to show a specific case where this relation fails to be symmetric, but this is the one that we listed. And then finally, what about transitive? Is this a transitive relation? What do we mean by transitive? Well, we need for all x, y, and z in the set A, we need when x, y is in R and y, z in R, this needs to imply that x, z is in R. So the way I like to think about this is I pick some element x, y in R, and then I find any other element y, z in R, but I need to make sure that the kind of interior coordinates match up, x, y, y, z. So they both match on that y dimension. So any pair of elements, x, y, and y, z, that I can find in R, the outer coordinates, x and z, better be an element of R. So that's what you do to kind of figure out if a relation is transitive. You find everything that pairs up, and then those outer coordinates better be an element of R. Well, again, this is obviously not a transitive relation because, for instance, 1 comma 3 is in R, and 3 comma 4 is in R. And notice they match up on this inner coordinate, so they both have a 3 right there. Since they both have a 3 right there, that means that this, the outer coordinates, 1 and 4, better be an element of R. So we need to have 1 comma 4 in R. But obviously 1 comma 4 is not in R. We can look at the set and see that it's not. So we found a specific case where this fails to be transitive, so this is not a transitive relation. And that is the end of the example.